We're going to continue on with the orbital motion. Now, much like centripetal acceleration, it will have similarities to understanding the direction of the acceleration due to gravity, always towards the center of your object. And we're going to need to remember that when we calculate our following problems. We have already determined that the gravitational field acting on the occupants of the space station and on the space station itself is not very different than the force acting on us. 8.8 versus 9.2. 9.82. It would not have been that much of a difference. But the question is, that 8.8 is still pretty significant when it comes to gravitational pull. So with an 8.8 gravitational field acting on you, why doesn't it fall to Earth? So as we had seen previously when we were talking about circular motion, your acceleration is always directed towards the center of the circle. The gravitational field will always be directed towards the center of the Earth and represents the acceleration that a mass would experience at any particular location on that circle. So if we look at this circle, no matter where we are on the circle, the path on that circle, every force is directed towards the center. But why doesn't it fall to Earth? Let's see on the next slide. If we recall, here we have, as you can see, the acceleration directed from the space station is always directed towards the center of the Earth. But the velocity of the space station is always going to be directed in a straight line. These two lines will always be perpendicular to themselves. So let's take a look at this diagram. I have an object that is traveling in a straight line around the orbit. What happens is that even though my velocity is going in a straight line away from the Earth, the gravitational acceleration is pulling it back towards the center. So I may continue out for a period of time, but I'm always being pulled back down. No matter where I am traveling on the circle, I can be traveling in a straight line, but the effect of gravity will always pull me back down, keeping me in an orbit around the Earth. But because it is traveling in a straight line, it will never fall back to Earth. The only circumstances is if something were to malfunction and that velocity would cease to exist. And then at that point, the gravity of the Earth would take over. But if we are in orbit, a satellite that is in orbit, it may travel 100 miles. But at that point is that it is then falling back to Earth based on how long it takes. So it may go out 100 miles and then fall back 10 miles. Go out 100 miles, fall back 10 miles to the Earth. But in an orbit, it is never that type of abrupt change. It is never going to be, so to speak, it's never going to be this type of zigzag motion. What happens is that it is in a constant relationship. So for every couple of miles it travels, it takes inches to go back into orbit. A couple of miles more, inches back to the orbit. It is never going to be this zigzag. It is a more fluid, which is a fluid curve, which is why orbits will tend to be in a more circular pattern, not something that is more rigid. So again, falling back to Earth and going down and falling back. So our orbits are not like that. Whoop. But in the large scale, it is something similar to that. It is something similar to that, where you are going out but coming down. But it happens on such a fluid basis that it's more about going out a couple of miles and falling back a couple of inches. It is constantly in motion. Newton decided that he wanted to, propose this theory about the velocity of objects in orbit. So he comes up with this thought experiment about firing a cannonball off the very high mountain. What happens is that for each cannonball that he fires from this mountaintop, they get increasing velocities. And with each increasing velocity, he's able to go further because the distance is acceleration is velocity changed over the distance. Okay, or change in velocity is the change in distance over time. So he keeps getting further and further in his path. What he theorizes or what he proposes is that he is able to fire a cannonball with enough velocity that he can not fall back to Earth. We actually knew that today as our escape velocity. That is how satellites are able to get fast enough out of the orbit and overcome the gravitational pull of the Earth's surface. So when a satellite is launched into the air, that firing of all of the rocket boosters has to deal with getting it out of the Earth's atmosphere, the Earth's orbit, fast enough so that the Earth does not overcome its escape velocity. Okay, so let's take a look at our next equation. Let's scooch this down a tiny bit. Now, we have forever seen for the last couple of months the force equals mass times acceleration. And we kind of see this thing because that was actually what we've just been practicing. Gravity times mass 1, mass 2 divided by radius squared. We have been practicing that for the last couple of weeks. But the question is, where does this come from? Well, if you recall that acceleration equals velocity squared over our radius, what happens is that this comes to that and is substituted back into here because we want to be able to manipulate our data with what we're given. Since we are talking about distances and we are talking about velocities and masses, we need to be able to put it into terms that we can work with. So if we are seeing that the mass times velocity squared over acceleration, well, I see a couple of like terms here. So it really doesn't matter, okay? And you'd actually have to look at each individual problem to find out which is the mass that you're talking about. The mass of the Earth, the mass of the object, okay? But in this case, we're just talking about that was a Freudian slip. We're talking about the mass of the object. So if I were to multiply each time by radius, each side by 1 radius, what this does is it gives me just a radius. It takes out the radius squared, and I'm simply left with then my mass on this side and the gravitational constant times the mass and a smaller mass and divided by the radius. So I have a mass here. And likewise, as like any other algebra problem, I am able to eliminate like terms. If I divide each side by m, they would eliminate out. Much like, again, I'm able to, cross off my r and my r on each side, leaving me with only an r and not an r squared on the bottom. I simplify my terms. Let me show you that one more time. Again, let me show you that one more time so that we have the full effect of that. I look at my r squared. Remember that this is r times r. And so let's simply replace that at this moment. If I multiply each side by r, I want to eliminate my variable on the denominator. So I multiply each side by r. And I multiply this side by r. Well, that then takes care of, that takes care of that r. And this r is eliminated by that r. I am then essentially left with g, a large mass, divided by an r equals m v squared. Now I can simplify my m's because in this case I want to take out an m on each side. And it's simply a reduction. So first I simplify my r's. Why I'm showing you is how we get from one equation that you already know into a new equation that you need to utilize in order to manipulate more difficult problems. So we're going to continue on. So I'm looking at my m squared divided by my r. I see that this is what I have here. And that this is what I have here. All I did was simplify. Now, like anything else that is r squared, I need to take the square root of both sides. And I am able to come up with my velocity equals my gravitational constant times the mass divided by its radius. Take a moment to get that down. Again, make sure you understand how you were able to eliminate your r's on the right side and reduce the r squared to an r on the left. You were able to eliminate like masses on both the left and the right, and that what remained on the left was the gravitational constant times the mass divided by a radius, and that was what was left on the right is a velocity squared. Take the square root of both sides and you come up with the equation velocity equals the square root of gm divided by r.